Hello, everybody. I'm Ishita Chakraborty. I'm an assistant professor of marketing at UW-Madison. First of all, thank you to AMA AISIG for giving me this unique opportunity to talk about a very interesting topic, which is multimodal data and its applications to marketing research. Let's begin with what is multimodal data. It is data that comes from multiple sources or channels and that needs to be analyzed together in order to derive insights. The sources could be text, images, voice, sensor data, for example, GPS trackers, and even structured data sources like tables and Excel sheets. Video data by nature is multimodal. For example, YouTube videos or Insta Reels often have components of text and images, voice, and so on. There are several applications of multimodal data analytics even outside of marketing. For example, healthcare. Medical data is often multimodal. So there's data from electronic health records, imaging data, sensor data, genomic data, and so on, all different modalities. And doctors often rely on this multimodal information to derive a common insight about the nature of the ailment, for example. Some other applications include autonomous cars, human computer interaction, example, robotics. Coming back to marketing, why is multimodal data exciting for a marketing researcher? One of the reasons is that there are several new video data sources due to the rise of both generation and consumption of video content. As per one of the papers published in 2020, YouTube users upload 100 hours of videos every minute. Hence, it's very important for marketers to understand that how do people consume video data, what drives consumption, engagement, and so on. The second reason is that, interestingly, even many traditional marketing data sources always had audiovisual components. Take the example of sales calls, focus groups, and advertisements. It's just that now we have the technology and computation power to analyze these videos at scale in a data-driven manner. And hence, the importance of multimodal data analytics for marketing researchers studying a variety of problems across domains. A little bit of literature recap. The multimodal data analysis falls in the larger umbrella of unstructured data analysis, which has been a growing research area within marketing. Initially, most of the research focused on text data and used dictionaries or what we call as domain-specific word list. These methods, they're quite interpretable but less scalable and could not model intricate details of language structure. And hence, slowly we saw the move towards machine learning and deep learning-based textual analytics, which brought a different kind of scale to the analysis. It enabled the analysis of millions of text reviews, social media tweets, and other market research data like in-depth interviews. With further technological advancements, we saw marketing researchers diving into other forms of or other modalities as well. There are some interesting research that has looked at voice data, both music as well as voice in something like crowdfunding videos, visual data, a lot of exciting work in the visual arena in the recent past. And more recently, we are also seeing a growing interest in incorporating multiple modalities in our research questions. For example, could be a combination of text and images, or a combination of text, images, and structured data. And of course, video analytics, which has text, images, vocal data, and also a timestamp. So we can see the progression of each of the modalities over time, which makes video analytics very interesting. What are some of the key takeaways from the table I was showing earlier? So one of the takeaways is that among single modalities, audio is comparatively less studied, and it's quite challenging to get interpretable features from audio data. Also, overall, there's still a lot of potential in the multimodal space. Most of the recent papers are in areas outside marketing. However, there are several marketing settings that have this type of data. So, with more data being available and technological progress, we would see like more and more work that analyzes different types of multimodal data. Now, let's dive into what are some of the typical challenges for multimodal data analysis. The first is the most common one. So these are messy and large data sets. Even a 20-minute video is roughly 5 to 7 pages of transcripts, around 4,000 words, has 30 to 35K visual frames. And just to give you a frame of reference, even a well-written online review has at the most 50 to 150 words, sometimes no images, at the most 4 to 6 images. So second, um, so this is just a lot more data. The second challenge is heterogeneity. So different types of data have different types of processing challenges. And not just that, they also have different privacy and storage requirements. For example, a company may be okay to store transcripts of an interview for longer, but not the videos themselves. And finally, the third challenge is redundancy versus complementarity of modalities. So, are the different modalities really adding complementary information or not? How does the typical analysis toolkit look like for multimodal analysis? It's generally a two-step process. The first step is feature extraction from each of the unimodal dimensions. So you have features extracted, say, from text, from images, and so on. How do you do the feature extraction? There are two dominant methodologies. The first one is domain-aware feature engineering, which means that using the knowledge that we have of specific domains, can we generate theoretically motivated features for each modality. For instance, we have a rich literature on persuasion and sales influence, and can we use that to create meaningful variables from every modality? The second most popular methodology is atheoretical and has more data requirement. It involves using existing pre-trained model for, say, text or image to create an embedding or representation for each of the constituent modalities, but it's highly scalable. Every method, as you can see, has strengths and weaknesses. For example, the first method is more apt when data size is a challenge, but there's a lot of extant domain knowledge in that particular area. It also leads to higher explainability. The second method is for more data-rich settings where domain knowledge is limited and explainability is not the major requirement, but you really care about about good prediction, and you have a large amount of data to train these models. The second step, once the unimodal features have been extracted, is how do we combine these features? In the first method, which is more domain-aware feature engineering, usually the number of features is limited, and we can directly input the extracted features into some kind of a classifier. And this is quite feasible. In the second method, which uses deep learning-based embeddings, there is an intermediate step, which is called as feature-level fusion, which involves projecting all the unimodal embeddings first into a common vector space. And this combined representation then goes to the final classifier. Let me give you some examples of each of these techniques now that I have used in some of my recent projects. Let's start with the first project, which is about using AI models for identifying sales persuasion skills from conversational videos collected during a real university recruitment process. The AI model in this paper is a domain-aware feature engineered multimodal model. This is joint work with my exceptional co-authors, Kai Cheong and Howard Dover at UT Dallas and K. Sudhir at Yale School of Management. So let me start with the motivation for the project before we dive into the details of the methodology. Motivation is that interviews are often necessary to identify the right candidates for jobs that involve soft skills like sales and marketing, as there is often not enough information in resumes to distinguish between good and bad candidates. Especially if it is entry level jobs, candidates can be very homogeneous in terms of experience and skill sets on paper. Second, post COVID, and even before that, there was a shift towards remote interviewing, and this was in turn generating a lot of high quality video data for firms. Now, given that hiring is a costly endeavor and something that firms need to engage in quite often, there is a lot of value in automating this process to some extent. And having this internal repository of past interviews, that firms have due to all these remote interviewing processes, these past interviews are already scored by experts. And having this repository scored by experts enables this kind of automation. Now, there are two interesting features of this particular setting, which motivates our choice for the multimodal model that we use. One, hiring is a high risk AI application. There's a lot of algorithmic aversion. Several US states and countries in Europe have laws around AI hiring. Second, unlike many marketing applications, so imagine customer reviews or social media, hiring typically has small data sets, and this has been documented in several OB literature. Thus, motivation for theory-driven feature engineering is very natural in this setting because there is a very high need for model explainability, and also there is usually limited and small size data sets. Now, let me talk about one interesting feature of the data that we have. So the data that we have here are conversational interviews, this being a sales interview context. And what's special about these videos is that unlike majority of social media videos where one person is speaking to an audience, these are two-sided conversations. They are also multi-instance in the sense that there are multiple back and forth communication turns. The second interesting thing is that this type of data set allows us to create certain features beyond standard text, image, and voice features. For example, we can measure conversational interactivity. How many turns were there in the conversation, whether there is an equal or unequal share of voice, when there is, between the two people. And we can also measure the extent of style matching, adaptation. So is one party changing their style in response to the other? And likewise, even body language cues can evolve with live feedback because it's back and forth communication. Now let me talk a little bit about our data and setting. So these are 195 videos from real sales interviews from a college campus in the US. Every video is a 15-minute sales role play for the same CRM software, where interviewee is the student and interviewer is a sales professional. There are real world stakes because if these students perform well, then they're likely to land an internship with one of the interviewing companies. Every interviewer conducts 5 to 8 interviews, and acts uniformly across these interviews. Finally, every interview is judged by 8 to 9 professional judges on various aspects, the key being persuasion. Our goal here is to build an AI model that can be a good predictor of an interviewee's success in the interview. So the question is, how do you use the different modalities to extract features of interest? We first divide the data into unimodal channels. The transcripts of the conversation is the source of the textual data, which enables to capture both content, what is spoken, and linguistic style. The audio enables capturing vocal style. The timestamp visuals, the frame by frame visuals of the interview help us to capture how body language evolves. We'll use all these modalities separately to construct unimodal features. I will not go through the details of all the feature creation process, but let me focus on some of the more interesting and novel ones. So let's talk about a very interesting feature of conversational videos, which is adaptation, which is known to be an important tactic in sales influence. In this paper, we focus on two dimensions of adaptation: style matching and active listening. What you see on your screen right now is an example of style matching. Here, the interviewer has a tendency to use the word absolutely more often. As a result, what we see after a few turns is that the interviewee also starts using the word absolutely more often than his or her actual style. Absolutely is just one example. More broadly, we are talking about certain classes of words, example, auxiliary verbs, that are known to give insight into subconscious style matching. Now, how do we measure this construct? We use a framework called Convocate, which, among many other functions, also helps to measure this particular construct of style matching over time. The second dimension of adaptation that we are interested in is active listening. Now, active listening is a pretty complex construct and comprises of sub-dimensions like paraphrasing, asking clarification questions, and showing interest in what is being said. There are no pre-existing tools to measure this dimension, and it's also hard to build a model to measure this using crowdsourced human labelers, as most lay people will not know to distinguish between good and bad active listening. Hence, here we take the help of a popular language model, GPT-4. Most language models have been trained on tasks like paraphrasing, so they already have some context of what it is. Further, to give them some domain knowledge, we use a very popular method, few-shot prompting, which involves giving the model some examples of the construct you wanted to identify. So now, the question is, how do we give good examples? For this, we rely on the scoring sheet of our expert judges. As seen in the figure in the right, some scoring sheets explicitly had comments about a student's active listening skills. We were able to identify both instances of good as well as bad active listening. These were then given as examples to GPT-4. And subsequently, the language model helped us to give an active listening score for each of the remaining video transcripts. The other novel features that we created from this data include body language elements. And to do this, we use OpenPose, which is an excellent tool to detect low-level features, that is, pixel positions of key body points with high accuracy. For every time frame, we get these pixel locations for the interviewer and interviewee separately. We then construct high-level, more interpretable features like distance between hands, posture, frequency of hand and head movements, to name a few. Let me show some live action of how OpenPose works for everybody here. In the above video, you can see that two people, you can see as the two people begin their conversation, this tool is able to capture their evolving key point locations for the visible areas, for example, hand, torso, and head. And that's how we get the key pixel positions at every timestamp for each of these two individuals. And we then specifically use the key point locations of the interviewee to construct features related to their hand movements, head movements, and so on. Now, how did our multimodal model do? in terms of performance? And what did we learn about the relative importance of different modalities? So, first, the good news, the model does reasonably well on selecting the right candidate or predicting their persuasion score. We learned that all modalities are important, content, what is said, being most important. The second most important modality is being interactive, which involves things like taking turns, active listening, and so on. We also learned that a moderate amount of hand gestures and head movements are good for persuasion. There are more detailed results about each of these features, and for that, I would encourage you to read the paper. The paper also has another part which involves combining AI intelligence with humans, and does that help or not? Though I won't go into the details of that part for the purpose of this presentation, let me give the main takeaway. So, the main takeaway from that analysis was that human in the loop helps, even having one human judge, especially to evaluate the early stages of the interview, improves prediction over the purely AI model, which means that there's still some elements of nonverbal communication that humans are able to identify better. We also find some interesting differences for what features matter more for male versus female interviewees. For example, head movement and active listening is more important for males, while politeness and collaborativeness are more important for female interviewees. For more details about our results and method, I would encourage you to look up our paper. It's available on SSRN, and it's forthcoming in Marketing Science. So hopefully some of you get a chance to read that paper. I will now briefly touch upon another of my recent working papers that uses multimodal data analysis. In this work, we are interested to predict the selling price for novice artwork. Novice artwork is art created by artists who do not have a strong brand yet. So, unlike masterpieces like a Picasso, they're not bought for investment, but rather for consumption. And hence, reputation is not the key factor influencing the price in these settings. Such artwork is often sold on platforms like Etsy.com. And on these platforms, there's several new artists who are often uncertain about what is the likely selling price for their product. And they rely on some crude online price calculators that use very basic features like a painting size and cost of material to arrive at a price. And so the question is, can we do better? Our empirical context is Etsy.com. It's one of the largest do-it-yourself art platforms in the United States. When an artist displays a painting on Etsy, there are several cues they can provide to prospective buyers. The dimensions of the painting, for example, being the simplest, but there are also textual cues here, like the painting title and description, and there are images of the artwork. And we want to use all these different data sources, text, images, structured data, to build a multimodal model that can predict price, sold price of art forms, artworks on Etsy. So how does our model look like? This is a deep learning based multimodal fusion model. Like I said earlier, this is a setting that is apt for a deep learning based fusion model as we have a reasonably big data set. In this study, we use 4,000 sold Etsy paintings from the abstract art genre. The other thing that motivates the use of a deep learning based fusion model is that we don't know ex ante much about what drives art pricing. Our deep learning model has a training data set of around 2,244 images, paintings, which in turn is 10,511 images, and a test data set of 562 paintings, which in turn has 2,810 images, which shows that many paintings have multiple images. The model has three types of inputs: structured data input, which are usually low dimensional compared to, say, text or image embeddings. And so we first use a multi-layer perceptron to make the dimensions comparable. The next set of input is the text embedding, which comes from the painting's title and description. And we use the OpenAI embeddings to come at a sentence embedding for the title and description. And finally, We use the images in the painting to create an image embedding. All this together is fused in the penultimate layer into one combined embedding, which is the input to the multimodal classifier that predicts the suggested price. In terms of model performance, what we learn is the full model that uses all the modalities has very good prediction power. We also do an ablation analysis. That is, we build the model by removing specific modalities, and we find that the highest loss of performance comes from removing the structured data followed by text data. Interestingly, the visual data is less important for this model's predictive performance. There's a lot more that we do in this paper. So for more details, read our paper. It's available on SSRN. There's also a cool online app that's associated with the paper. We call it the Etsy Price Estimator. You can check that out. Finally, I want to leave you with some thoughts on what is next in multimodal data analysis. What we are seeing now is a surge in a lot of general purpose multimodal LLMs, MLLMs, that are able to match the performance of task-specific models that we have relied on for many years in the past. LLMs are well known by now. They are large language model, trains on millions of documents, and capable of many general purpose language tasks, for example, translation or paraphrasing, example GPT-4. What happened with the popularity of LLMs was that there was a push in both industry and academia to develop multimodal LLMs, which is an LLM model, but with the ability to receive, reason, and output multimodal information. This is a very new and upcoming field, and I am experimenting with some of these MLLMs myself, very early stage work. There are some excellent review papers on MLLMs now. I mentioned one of them in the slide. This particular paper also has a pretty updated GitHub page. Just to give a very brief background, how do we think about an MLLM? It's generally 3 modules. The first module is a pre-trained modality encoder. And there is a pre-trained LLM associated with it. And connecting the two is a modality interface. As the authors of this review paper explain, and I think it's a very nice analogy, we can think of the encoder unit like the eyes and ears of a human, and it takes in different types of signals, audio signals, video signals, so on. The connector is like the neurons that take these signals to the brain, which is the LLM or large language model. Just like the human brains, they understand and reason the processed signals. And finally, the LLM output can again be either in the form of text, which is the natural output for an LLM, or it could be in any other modality. The modality conversion is done by using a generator unit. So MLLMs have a lot of promise for multimodal data analysis, and they would become a very important research toolkit in the times to come. And so it would be a very good idea to check out some of these review papers on MLLMs if you're interested to work on multimodal data. With this, I would stop here. For any further questions, feel free to reach out to me on my email address. You can also check out my research page. And once again, thank you very much to AMA AISIG